Dear students, after studying this module, you shall be able to know about what is regioselectivity. Understand the basic difference between regioselectivity and chemoselectivity and identify the regioselectivity in various reactions and calculate the regioselectivity for a particular reaction. What is regioselectivity? Regioselectivity is known as the preference chemical bond breaking or making in one direction of overall other possible directions. It is certainly applicable to positions which many reagents affect during the course of reaction. An example to consider is which proton a strong base will abstract from an organic molecule, or where a substituted benzene ring a further substituent will add. If there occurs preponderance over which regioisomer will be formed, then that reaction can be termed as regioselective. A particular example is when 2-propenyl benzene reacts with N-bromosuccinamide, it gives bromonium ion, and followed by aqueous acetone gives halohydrin, 2 as major and 3 as a minor product. Another example is 1-methylcyclohexene when react with bromine and formation of a cyclic bromonium ion and followed by ring opening of the bromonium ion by water prefers to give 2-bromo-1-methylcyclohexanol, which is 5, as the major product. If there is a possibility of more than one reaction occurring between a set of reactants under the reaction conditions which are same, giving products that are constitutional isomers, and if one product is formed in greater amounts than the others, the reaction is therefore summed up to be regioselective reaction. Different examples of regioselective reactions. Regioselectivity in addition reactions. On the previous modules of addition, we talked about the basic pattern followed in the addition reactions: breaking of the carbon-carbon double bond, formation of two new bonds to the adjacent carbons, and how this is the exact position pattern of the elimination reactions we have discussed earlier. Addition of HBr to alkene. Addition of HBr to 1-methylcyclohexene is a regioselective reaction because it favors the formation of a bond between the alkene's tertiary carbon and the bromine atom instead of alkene's secondary carbon. This regioselectivity happens to form the basis of the Markovnikov rule. As shown, it gives the major and the minor products as the bromomethyl at one position and bromomethyl at two different positions. The addition reaction favors the formation of a more stable intermediate, and consequently the product formed is also the more stable intermediate. Therefore, the major product of the addition of HBr, where bromine is some atom more electronegative than hydrogen, to a 1-methylcyclohexene, has the hydrogen atom in the less substituted position and bromine in the more substituted position. However, the less stable carbocation, which is also less substituted, will still be formed to some extent and will proceed to form the minor product with the opposite attachment of bromine. Hydroboration reaction and addition of hydrogen and bromine to alkenes. Hydroboration oxidation is a reaction which follows an anti-Markovnikov rule, with the boron attaching to the less substituted carbon. The hydroxyl group is coming from the hydrogen peroxide and sodium hydroxide. The hydrogen and the hydroxyl groups are added in the syn addition, leading to the cis stereochemistry. In this reaction, it's observed that the product 9, which is formed in much higher yield than the product 10. The hydroboration reaction is one of the simple addition reaction which proceeds cleanly in a syn fashion. The hydroboration reaction is a single step reaction in which the bonding of the double bond to carbons to boron and hydrogen is concerted. Thus, from this information we can conclude that the geometry of the addition must be syn. Since a discrete carbocation intermediate is never formed, rearrangements are a rare possibility. These features are clearly displayed for the hydroboration reaction of alpha-pinene. No rearrangements, and henceforth a regioselective addition reaction is taking place. The hydroboration reaction is most commonly used to hydrate alkenes in an anti-Markovnikov fashion. Thus, we also need to be aware of the stereoselectivity of the second oxidation reaction, which involves the substitution of a hydroxyl group for the boron atom. Some independent studies have also shown this reaction occurs with the retention of configuration, so the overall addition of water is also syn. The hydroboration of alpha-pinene also provides a fine example of steric hindrance control in the chemical reactions. Considering the case of lesser complex alkenes employed in the earlier examples, the plane of the double bond was often a plane of symmetry, and the addition reagents could approach with equal ease from either side. In this case, the phase of the double bond is covered by one of the methyl groups bonded to carbon 6, blocking any approach from that side. Thus, the reagents trying to add to this double bond must therefore approach from the side opposite to the methyl. Not all the addition reactions produce regioisomer. For example, hydrogenation treatment of alkenes with metal catalyst, that is palladium over carbon or palladium charcoal, and hydrogen gas gives the following products. Since we are forming a carbon-hydrogen bond on both the sides of the alkene, it is not possible to form regioisomers here because it will only give only one product, that is 1-methyl cyclohexane. The same is the case for the addition of bromine to alkenes. Since we are forming carbon-bromine on both the carbons, regioselectivity does not occur because it produces only a single product, which is 1,2-dibromo-1-methyl cyclohexane. Baeyer-Villiger oxidation. The Baeyer-Villiger oxidation is known to oxidize ketones to esters by employing peroxy acids. The Baeyer-Villiger rearrangement is a regioselective reaction. In the aforementioned case discussed, the R' group is presumed to have greater migratory aptitude, and thus preferentially only one product is formed. This reaction involves the oxidative cleavage of a carbon-carbon bond. The aldehydes may yield carboxylic acid or formates. In the latter case, alcohols are the final products due to hydrolysis of the unstable formates under the reaction conditions. Cyclic ketones yield lactones, which are the cyclic esters. The Baeyer-Villiger oxidation is in bicyclo 2,2,1 heptane 2-one in the presence of peracids give lactones. Looking into the mechanism of this oxidation reaction, the peroxy group initially adds to the carbonyl carbon to give a Krigi-like intermediate. Subsequently, one of the group attached to the carbonyl carbon migrates to the electron deficient oxygen atom in the rate determining concerted step, which is the rate determining step. These substituents which can stabilize the positive charge can migrate more readily. The migratory aptitude of various substituents follows the following order: 3-degree alkyl greater than the cyclohexyl, in turn which is greater than the 2-degree alkyls, benzyl aryl 1-degree alkyl, and finally the methyl group. The electron withdrawing groups with the -I, that is inductive groups on the peroxy acids, enhance the rate of reaction. As the rearrangement is a concerted process, the configuration of the migrating chiral substituent is retained. In case of aldehydes, usually the hydrogen atom is migrated preferentially and thus by furnishing carboxylic acids. But formates are also produced when the migrating group is other than the hydrogen. This is possible when the other substituent is a tertiary alkyl group or electron-rich vinyl or aryl group, as in the examples for the Alkene reaction. Formation of epoxide is one of the competing reactions. When a double bond is present in the molecule, especially at low temperatures in neutral solvents. Birch reduction. In Birch reduction, where the radical anion is protonated, initially determines the structure of product. With an electron donor such as methoxy, alkyl protonation has been thought by some investigator as being ortho, which is adjacent or at 1,2 position to the substituent. Other investigators have thought the protonation is meta, that is 1,3 substituent. With the electron withdrawing substituents such as carboxylic acids, the protonation has been thought to come at the site ipso of the substituent or the para, where that is 1,4 substitution. Electrophilic aromatic substitution. Aromatic electrophilic substitution of toluene in the presence of nitrous acid with acetic anhydrides to give 1-methyl-4-nitrobenzene in 34% yield and 1-methyl-2-nitrobenzene in 63% yield. Since the electron donating groups are ring activators, they direct the incoming electrophiles to the ortho or para positions. This is a clear example of regioselectivity. The mechanistic details of the ortho attack, para and the meta attack are shown here in the given mechanisms. Diels-Alder reaction. In the Diels-Alder reaction, a diene bearing an electron donating group at C1 has its largest HOMO coefficient at C4, while the dienophile has the largest LUMO coefficient at C2. Pairing these two coefficients gives 1,2-methyl-cyclohex-3-enyl ethanone product as major and 1,5-methyl-cyclohex-3-enyl ethanone product as the minor product. Friedel-Crafts reaction. Friedel-Crafts reaction in 4,4-dimethyl-cyclohex-1-enyl trimethylsilane by using acetyl chloride with aluminium trichloride to give 1,4,4-dimethyl-cyclohex-1-enyl ethanone. Regioselectivity of elimination. Preferential reaction at one site of a single functional group over other sites that could undergo the same reaction. This type of selectivity is also seen in elimination. It is well established that alkene stability is influenced by degree of substitution of the double bond. The greater number of carbons attached to the double bond, more stable it is and is seen in these reactions. It can be seen that the more substituted alkenes are formed in the higher percentage as compared to the minor products which contain a less substituted alkene. Now, How to determine the regioselectivity? The ring opening of 1,2-epoxyhexane with methanol using iron cyclopropyl boron fluoride as a catalyst gives rise to regioisomers 1-methoxyhexane 2-ol and 2-methoxyhexane 1-ol. The ratio of these two regioisomers in terms of percentage area were determined by gas chromatography. To summarize, regioselectivity is the preference of one direction of the chemical bond making or breaking over all other possible directions. If there is a preponderance over which regioisomer will be formed, then that reaction can be termed as regioselective. In this module, we have discussed the regioselectivity in various types of reactions such as addition of HBr to alkenes, hydroboration reaction and addition of hydrogen and bromine to alkenes, Baeyer-Villiger oxidation, Birch reduction, electrophilic aromatic substitution, Diels-Alder reaction, Friedel-Crafts reaction and regioselectivity involved in elimination. Various methods, one of which is gas chromatography, is used for calculating the regioselectivity for many substrates.